Hey everyone, this will be a short video looking at vascular resistance, and I've noticed that I'm kind of out of the view of the camera. I'm going to pull this down a little bit. I think that might be better. Yeah. So when looking at vascular resistance, we need to keep in mind that we're actually calculating a resistance value for two separate vasculatures. We can capture the vascular resistance here systemically, but we can also look at values in the pulmonary circuit as well. So you just have to be very careful and make sure that you defined which vasculature that you're determining the vascular resistance for. You'll see some new words on here, some new terminology. This one right here is the pulmonary capillary wedge pressure, the PCWP, which we'll talk about in class. There's the spelling of it to help out a little bit. The PCWP, or the pulmonary capillary wedge pressure, it's a pressure that you see the arrow pointing to the left heart. It's reflective of left heart values. For you guys who've been studying, you'll know that this 8 torr is a normal pulmonary vein pressure. The pulmonary vein pressure is the pressure that moves the blood into this left atria, and we can define that by determining the pulmonary capillary wedge pressure. And I'll show you how we do that in class. It's really pretty interesting. But the normal PCWP, or pulmonary capillary wedge pressure, is somewhere around 4 to 12 torr. We work with a lot of ranges in respiratory care, by the way. So just something to kind of get used to. But 4 to 12, if you think of it mathematically, the middle number would be about 8. 8's in between 4 and 12. So 8 torr is a normal PCWP, which is reflective of pulmonary vein or left heart pressures. Really neat stuff, and I'll show you that later. But here's the spelling. Make sure you get that. There's different ways to call this pulmonary artery occlusive pressure. Some just call it the PWP, the pulmonary wedge pressure. So just different names, but we'll look at that in class. Another item up here is what I have here for cardiac output. Cardiac output, and some of you may know this already, but it's the total amount of blood that the heart can eject in 1 minute. So the value I have here for cardiac output is 5 liters per minute, and I can determine that amount of cardiac output. The abbreviation is QT. I can determine that amount by counting the patient's heart rate and then multiplying that by the amount of volume that comes out at each contraction, which is called stroke volume. Each stroke, there's a volume that comes out. And if I can measure that volume, multiply it by the heart rate, then I can determine the cardiac output. Cardiac output's important because we're going to use that as our flow. And flow is needed, as you see from the vascular resistance equations that we're going to be looking at. Okay. Otherwise, we know the rest of the material. You've got a mean arterial blood pressure of about 93 torr. On the other side of the systemic loop, you've got a CVP of about 4 torr. That's within our 2 to 6 range torr for CVP. Pulmonary artery mean is 15 torr that we talked about already. 25 over 10, we did the average, it's 15. And then we're going to use PCWP, which is reflective of left heart values. And we're going to use the middle number of the range, 4 to 12, we'll use as an 8. Okay? The calculations for resistance are actually pretty easy once you've kind of practiced them a little bit. All you're going to do is determine what the pressure gradient is, and you guys remember doing the pressure gradients this morning in class, and then you're going to put that over the flow. Flow is another way to describe cardiac output. It's the flow of blood moving through the loop every minute. All right, so P, change in P, over V dot. V dot is flow. All right. So the equation is pretty easy once you remember that. You just have to determine the delta P. If we're going to do it systemically, we're going to call that the systemic vascular resistance. The systemic vascular resistance has the pressure gradient, the delta P, which is going to be 93 torr minus 4 torr. Okay. So we've got the delta P over the flow. The flow rate is going to be 5 liters per minute, just because that's what I'm telling you it is. Okay. We get our trusty calculator. We do the math. 93 minus 4 equals 89. So we've got 89 torr, right, over 5 liters a minute. And we solve for that. 89 divided by 5 equals 17.8. Alright, and then the unit of measure is millimeters of mercury, or torr over liters per minute. So it'd be 17.8 torr over liters per minute. And we've just calculated the systemic vascular resistance. That's the value. All right, cool. For pulmonary vascular resistance, we're going to do the same thing. We're just going to use the pressure gradient in the pulmonary circuit. So this would be pulmonary vascular resistance. We're going to find the delta P that's established. So we've got 15 on the high end. Got 15 torr minus the PCWP, which we're going to use as 8 because these are just normal values, and divide by the flow rate, which is liters per minute. So delta P over the flow. Pretty easy. You do the math. 15 minus 8 is 7, because I can do that in my head, over 5. 7 divided by 5 is 1 point, what is that, y'all? 1 point something? I think I'd know that, huh? 1.4, you do that again. 7 divided by 5. There you go. 1.4 torr over liter per minute. And we've solved for PVR. Thanks.